Thanks so much. So today we're delighted to have Alexander Campbell from the Sydney office of MSRI to tell us about Joyal's cylinder conjecture.
Well, thank you very much, Emily, and thanks to the seminar organizers and the MSRI staff for making this possible. I'd like to reiterate Emily's point, so please do interrupt with questions or comments. We've got plenty of time. It's also 7 a.m. in Sydney, so if I'm a bit slow, it's because I'm only half awake right now.
Alex,
yeah,
sorry, a quick question before we begin. Are your slides on the web anywhere?
No. I could email them to people, but yeah, I don't have time. But I just prepared them, so
okay.
I haven't put them up anywhere yet. Sorry,
No
I can put them up afterwards.
Well, great, thank you.
Yeah. Okay. Yes, so I'll be speaking about Joyal's cylinder conjecture, about which I wrote a preprint late last year. So let me tell you first the structure of the talk. So it will be in 3 parts. So the first part of the talk will be to give the necessary background just to the statement of the conjecture. Originally this talk was planned for the joint newcomers seminar, which was for both programs. So I did want to make it inclusive to people from different backgrounds. And once we've stated the conjecture, I will give an overview of the proof that I gave in this preprint. And finally, I'll give an application of the proof of the conjecture to a result which I'll describe when we get to it. All right, so first we've got the section on the background. So let's, as a bit of motivation, let's recall some classical category theory. So if I've got a pair of categories A and B, I can define a profunctor from A to B to be a functor from A opt times B into set. You can think about this as you can think about a profunctor between categories as a categorification of a relation between sets. So between any objects in A and any object in B, I get a set of ways in which they're related. Now, given a profunctor, which are called M, I can construct a category called its collage. The objects of this collage category is the objects of A and B. So the set of objects of the collage is the disjoint union of the sets of objects of the categories A and B. So I've got 2 kinds of objects, the objects in A, the objects in B, and I have various kinds of morphisms. So the categories A and B sit as full subcategories inside this collage. So between any 2 objects of A, I've got their morphisms as in the category A. For any 2 objects in B, I've got the morphisms as in B. But now there's this new kind of morphism coming from the profunctor. So between any object X in the category A and any object Y in the category B, I have this set M of X, Y coming from the profunctor, which is giving a new notion of morphism in this collage category. And there are no morphisms going from an object of B to an object of A. And the composition in this category is defined using the compositions in the categories A and B, and also via the value of this profunctor, this functor, on the morphisms of A and B. So if you like, there are 2 kinds of objects, there are 3 kinds of morphisms, and there are sort of 4 kinds of composable pairs. Were this a board talk, I'd be able to draw all these things, but let's move on. So there's a unique functor from the collage category to the poset 0 less than 1, which sends every object of A to the object 0 and sends every object of B to the object 1. So the fibers of this functor over the objects 0 and 1 are precisely these categories A and B, as drawn at the bottom of the page here. And this construction gives an equivalence of categories between the profunctors between A and B and these categories over the poset 0 less than 1, whose fibers over 0 and 1 are A and B. So this is a classical bit of category theory, and this will motivate the definition of a cylinder on the next page. So we now move into the world of simplicial sets. A and B are now a pair of simplicial sets, and I define a cylinder from A to B to be a simplicial set X over the simplicial set delta 1, which is the nerve of this poset 0 less than 1. And the requirement is that the fiber of this map over the object 0 is this simplicial set A, and the fiber over 1 is the simplicial set B. So exactly formally the same as we had on the previous slide. And so that's what a cylinder from A to B is, and I can define the category of cylinders from A to B to have these cylinders from A to B as objects, and morphisms are morphisms of simplicial sets over delta 1, which are the identity on the two fibers. Or I could define it formally as the fiber of this functor is displayed. Now, again, if I could draw pictures, I would, but let's just, I'll describe what a cylinder looks like. So in this simplicial set X, there are two kinds of zero simplices. There's those belonging to the simplicial set A, and those belonging to the simplicial set B. There are now three kinds of one simplex. There's, again, those belonging to the simplicial set A, those belonging to B, but there are now these sort of bridging simplices, which go from some zero simplex of A to some zero simplex of B. So exactly as we had the morphisms in the collage of a profunctor. And now there's four kinds of two simplices in the cylinder. Again, there's the ones belonging to A, the ones belonging to B, and two simplices you could sort of think about as being like composable pairs. And so we've also got, you know, formally I'm thinking about it in terms of its spine. So I could have a pair of one simplices in A as the spine. I could have a pair of one simplices in B as the spine of the two simplex, or I could have, a one simplex in A, or one of these bridging one simplices going from A to B, or one of these bridging one simplices going from A to B and one simplex in B, and so on. Now, it'll be important for the story that follows to identify the terminal object of the category of cylinders from A to B. So it's not hard to see that the initial object is just the disjoint union of A and B. So there are no, you know, bridging simplices. We've just got A and B and nothing going on between them. Now, the join, I've written a formula for the join below, but one way we might describe it is that we've got the simplicial sets A and B, and for any simplex in A and any simplex in B, there's precisely one of these new simplices bridging them. Now, formally, we've got this formula at the bottom of the slides. So, yeah, if you play with that formula, you'll see that it means precisely this, that there's precisely one kind of simplex bridging each simplex of A to each simplex of B.
Alex, can I interrupt?
Yeah. Yes, please.
So here's a fact that I learned this week, and it's actually a result of Andre Joyal in one of his quasi-categories notes. But the functor that you've displayed in the middle of this slide is pull back along the boundary inclusion. So since simplicial sets is locally Cartesian closed, this has both left and right adjoints. And you can compute that up to isomorphism, if you take the right adjoint, which is push forward along that boundary inclusion, and apply it to the map from A and B over 2 points, you compute exactly the join.
And yeah, so that's, this right adjoint is precisely picking up the terminal objects in the fibers of this map, which is the terminal objects of these categories, CIL A, B, as I've written them. Yeah, so if you like, that's the definition of the join, and then at the bottom is just a formula for the simplices of the join. But let's move on.
Maybe just one observation,
Sure.
a trivial observation. Of course, the join of two category is kind of categorical versions of the join operations between spaces the topologists are using.
Mm-hmm.
Where you put between any 2 points an edge, and etc. Yeah,
precisely.
So, for example, a cone is a special case of a join. And,
yeah. That's right. So, just a bit of notation. So, for any simplicial set C, let me denote the category of simplices of C by delta over C. So, this is the category whose objects are all the simplices in C, and there's various morphisms relating them by these face intergeneracy maps. Now, an absolutely fundamental observation of Joyal for this story is that the category of cylinders between any two simplicial sets A and B, this category still A, B, is actually a presheaf category. It's equivalent to the category of presheaves over the product of the categories of simplices of A and B, as displayed here. I'm using square brackets to denote functor categories. Now, I've written here what this equivalence does. So if I've got some cylinder X, and I've denoted this map from X to the join of A and B by P. So what presheaf on this product of the categories of simplices of A and B does this correspond to? So, well, its value at a pair of simplices alpha and beta, I've noticed I've got typos here, alpha belongs to A and beta belongs to B. But we can understand what the set of, that this corresponding presheaf sends this pair to as the set of m plus 1 plus n simplices of X, say sigma, such that this bottom diagram commutes. Now, where does m plus 1 plus n come from? Well, it's important to note that the join of the m simplex and the n simplex is the m plus 1 plus n simplex. Again, in low dimensions, it would be helpful to draw examples, but it's a little bit difficult in this situation. But this equivalence of categories between SIL AB and this presheaf category will become very important later on in the story. So I just wanted to introduce this straight away. So regretfully, I can't really draw all these pictures for you, but I encourage you later, if you're interested, to play around with them. It gives an absolutely great intuition for what these cylinders really are. Now, from this equivalence of categories, we get further equivalences of categories. So at the bottom of the slide here, the one on the left will be the one that we are really using later in the story. So there's equivalence between cylinders from A to B in a certain functor category. I'll describe that when we get to it. And on the bottom right is another equivalence. One can also think of cylinders from A to B as being bisimplicial sets over the exterior product of A and B, but that won't play a part in our story. All right. Now, a bit of background. So this conjecture that I'm about to describe concerns model categories and model structures. So let me recall for everyone what these are. So a model structure on a category, which is usually presumed to be complete and co-complete, consists of three classes of morphisms in the category called weak equivalences, co-fibrations, and fibrations. And these are subject to various axioms, which I won't recall. Now, the point of the model structure on a category is that it enables one to do homotopy theory within that category. We'll see some examples on the next slide. And a category equipped with the model structure is called a model category. Now, this conjecture, which we're about to describe, concerns the fibrant objects of a certain model category. So an object of a model category is said to be fibrant if the unique morphism from it to the terminal object is a fibration. Now, a very useful lemma and important for our story is that, so a model structure is formed from these three classes of morphisms, but one can determine the rest of the structure from some proper subset of it. So for instance, if I know the co-fibrations and the weak equivalences of a model structure, then I can figure out what the fibrations are. Similarly, I can determine a model structure just from its co-fibrations and its class of fibrant objects. So these are sort of standard and very useful lemmas in model category theory. All right, so an important example of a model category. So on the category of simplicial sets, there is a model structure due to Joyal. So its fibrant objects are the quasi-categories. So these are the simplicial sets written X, which have the right lifting property with respect to the inner horn inclusions. I suspect we've seen this a number of times in various workshops and seminars this semester. And I'll also need a sort of relative version of the notion of quasi-category. So I say that a morphism of simplicial sets P from X to Y is an inner fibration if it has the right lifting property with respect to the inner horn inclusions. Okay, so, and at the bottom of the slide, I've described this Joyal's model structure for quasi-categories. So this is that unique model structure on the category of simplicial sets whose co-fibrations are the monomorphisms and whose fibrant objects are the quasi-categories. So as on the previous slide, that determines the rest of the model structure. In particular, there's a class of weak equivalences, which are called weak categorical equivalences. And a result of Joyal is that we can characterize the fibrations between quasi-categories, fibrations between fiber and objects, in a very explicit way. These are the so-called isofibrations. They're the inner fibrations which have an isomorphism lifting property, which is described below. And I should note that we don't have such an explicit description of the fibrations between arbitrary simplicial sets. I'll say more about that later, as that'll be an important part of the story. Okay, so this is the Joyal model structure on the category of simplicial sets, which I might also call the model structure for quasi-categories. So I'm now able to pose the conjecture. Now this concerns another model structure. So let A and B be a pair of simplicial sets. We define this category Sil AB, or cylinders from A to B. Now, Joyal described the model structure on this category, which is sort of created via the model structure for quasi-categories on simplicial sets. So there's this forgetful functor from the category of cylinders from A to B to the category of simplicial sets, which, if we think about this cylinder as a simplicial set over delta 1 with certain fibers, we just remember the simplicial set. So this defines a functor. And Joyal described this model structure on Sil AB, and the weak equivalences, cofibrations, and fibrations, these classes of morphisms described in the model structure, are just those morphisms in Sil AB whose underlying morphism of simplicial sets is a weak equivalence, cofibration, or fibration in the model structure for quasi-categories on the category of simplicial sets. So, for instance, by definition, an object, a cylinder X in Sil AB, is a fibrant object in this model structure, if and only if that canonical morphism X to the join of A and B, which we'll call as the terminal object in the category of cylinders from A to B, if and only if that canonical morphism is a fibration in the model structure for quasi-categories. Now, I will refer to this model structure on Sil AB as the Joyal model structure on Sil AB. And it's about this, it's this model structure about which Joyal made the following conjecture in his notes on quasi-categories. So there's two parts. So the first part is that a cylinder X in the category Sil AB is fibrant. It's a fibrant object in this model structure, if and only if that canonical morphism is an inner fibration. So we know by definition that it's fibrant if and only if it's a fibration in the Joyal model structure. But the conjecture is that in fact it's fibrant if and only if it's an inner fibration. And the second half of the conjecture is that a morphism between fibrant cylinders is a fibration in the model structure, if and only if it's an inner fibration. Okay.
So Alex, can I test my understanding? Yeah. So if A and B are quasi-categories, I think this is true.
Yes. Well, the point of the talk is that it's always true, but you're very observant, because in fact, when A and B are quasi-categories, this is very easy to prove, as I have on this slide here. So I've called this the easy case of Joyal's cylinder conjecture. And this is a very easy exercise. And it's because we have this very nice description of what the fibrations between quasi-categories are. So, so in this, so the lemma is just the case of Joyal's cylinder conjecture in which A and B are quasi-categories. So then it's very easy to prove that a cylinder is fibrant if and only if that canonical morphism to the join is an inner fibration. Similarly, this fact about this characterization of the fibrations between fibrant objects. And I can very quickly run through the gist of the argument. So, of course, one direction is trivial. So let's suppose, because every fibration is an inner fibration by definition. So for the converse, suppose that this canonical morphism P from X to the join is an inner fibration. So I want to prove that it's a fibration. Well, because A and B are quasi-categories, their join is also a quasi-category. And so I just have to prove that this map has that isomorphism lifting property. But the only isomorphisms in the join belong either to that simplicial set A or the simplicial set B. And the fibers of this map P above A and B are just A and B. So there's a unique lift of that isomorphism. So that's very easy. And it's similarly very easy to prove the characterization of fibrations between fibrant objects. So when A and B are quasi-categories, no trouble. But when A and B are not quasi-categories, then it's much more difficult, because we don't have this easy to check explicit description of the fibrations in the model structure for quasi-categories between arbitrary simplicial sets. Now let me just make an aside. So for many years it was an open question. So this is a very sort of technical remark, so be aware. So for many years it was an open question whether the class of inner anodyne maps of simplicial sets could be characterized as those maps which have three properties, that they're monomorphisms, that they're bijective on zero simplicities, and that they're weak categorical equivalences. Had the answer to that question turned out to be yes, that is a characterization of the inner anodyne maps, then the general case of Joyal's cylinder conjecture would be basically as easy to prove as the special case in which A and B are quasi-categories. However, that's unfortunately not so. This characterization, this isn't a characterization of the class of inner anodyne maps, as I recently proved by producing a counterexample. Got a reference to this that was published recently in the Proceedings of the American Mathematical Society. So the conclusion is that we need some new kind of arguments to prove the general case of Joyal's cylinder conjecture. And that's what I now want to describe to you. And I've got here the archive identifier of the preprint in which you can find the detailed argument. So we're about to move on to a new section, so maybe I should pause and ask for any questions at this moment before we delve into the proof. No? All right. So now I'll just give you an overview of the proof.
I have a quick question.
Please, yeah.
For no other reason to remind some of us.
Hi.
So if the base,
Hi, David.
hi Andre. If there's a map between simplicial sets where the base is a quasi-category, am I remembering correctly that it's fibrant in Joyal's model structure if and only if it restricts to maximal subcon complexes as a confibration and it's an inner fibration?
That's right, yeah.
Okay.
Yeah, so that restriction to be a confibration between the maximal to the cores, that gives you this isomorphism lifting property. That's
right. So that's why Emily was so quick to note that it's like, so then a follow-up to that is do you know has anyone conjectured a similar version to the conjecture you're speaking to over, say, bracket classifying categories over bracket 2 with specified restrictions over each vertex of bracket 2?
Well, that's essentially what this conjecture will be. So we'll see that yeah, so this is the content of the conjecture basically. We'll see that for one of these cylinders or correspondences X between two simplicial sets A and B, this map from that simplicial set to the join of A and B, for it to be a fibration in Joyal's model structure, it suffices for it to be an inner fibration. I'm not sure if that was your question.
Parameterized joins characterize objects over over bracket 1. And I was extending this discussion to bracket 2. I don't mean to distract too much. In fact, I suggest that we ignore.
No, I haven't thought about that. Yeah.
Thanks.
Right. Yeah. So my name for the category, the post said 0 less than 1 is 2. So I think when you said 2, I heard what you would call 1. All right. But yeah, let me now give an overview of the proof of the conjecture. So I'll describe the proof in 5 steps. We'll go through it nice and slowly. All right, so the first step. So we had this Joyal model structure on Sil AB, about which we made this conjecture. So the first step is to construct another model structure on Sil AB, which I'm calling the ambivariant model structure for a reason I won't necessarily go into. And this is characterized by the properties that it has the same co-fibrations as the Joyal model structure on Sil AB, namely the monomorphisms. But its fibrant objects and fibrations between fibrant objects are precisely as described in Joyal's conjecture. So the objects, the fibrant objects are those objects X, whose canonical map to the join of A and B is an inner fibration. These are the fibrant objects in this ambivariant model structure on Sil AB. And similarly, the fibrations between fibrant objects are precisely the inner fibrations. So the first step of the proof is to construct this other model structure on SIL AB. And there's a number of ways to do this. And in the paper, I do this for those who like to construct model structures. Let me just spell this out. So I construct this ambivariant model structure on SIL AB by doing a transfer of model structures from another model structure on the category of simplicial sets over the join of A and B. So I call this the parameterized Joyal model structure on that slice category. So generally, for any simplicial set C, I construct in the appendix to this preprint a model structure on the slice category of simplicial sets over C, which I call the parameterized Joyal model structure, in which characterized by its cofibrations being the monomorphisms and its fibrin objects being the inner fibrations with codomain C. So this is, there's a number of model structures of this kind that one encounters in quasi-category theory. So for instance, there's a model structure where the fibrin objects are the left fibrations with fixed codomain, or right fibrations with fixed codomain, or even the fibrations in the Joyal model structure with fixed codomain. But for this particular purpose, I found that it was, and this new model structure where the fibrin objects are the inner fibrations with codomain C was useful. And in the appendix, I used this new family of model structures to prove a bunch of results, and also to give new proofs of older results. So you can see the appendix if you're interested. But there are a number of other ways that one could construct this ambivariant model structure, as I described somewhere in the paper. So that's step one. We sort of construct this other model structure where the Joyal cylinder conjecture is sort of true just by fiat. And so step two of the proof is just to show that these two model structures, the Joyal and the ambivariant model structures on SIL AB, are actually the same model structure. So that's step two, is we observe that that's an equivalent statement of this conjecture which we would like to prove. So in particular, since we know Joyal's cylinder conjecture is true if A and B are quasi-categories, we know that if A and B are quasi-categories, that this Joyal and ambivariant model structures coincide. They are the same on the category SIL AB. Okay. Now, the next step, step three in the argument, uses this lemma that we mentioned earlier about characterizing model structures, either just from their cofibrations and weak equivalences, or just by their cofibrations and fibrin objects. So let me just say this step three. And so this just follows from that lemma about model categories, and from the fact that any fibration in the model structure of a quasi-category is in particular an inner fibration. So it follows by a kind of Galois connection that every ambivariant equivalence in SIL AB, that is every weak equivalence in the ambivariant model structure, is in particular a weak categorical equivalence, weak equivalence in Joyal's model structure. And so it remains to prove the converse, that any weak categorical equivalence between cylinders in the category SIL AB is an ambivariant equivalence. So once we prove that, we can prove that the model structures are the same, and hence that Joyal's conjecture is true. And so how do we prove that? Well, this is where things begin to get a bit technical. So remember, we're wanting to prove that every weak categorical equivalence in SIL AB is an ambivariant equivalence. All right, so step four. So since we know that the conjecture is true when A and B are quasi-categories, essentially we're going to try to reduce to that case. And we'll do that in the final step by using properties of a certain change of base functor. So if I have a pair of morphisms of simplicial sets, so U going from A to A prime and V going from B to B prime, then I can define a kind of push out or push forward functor from the category of cylinders from A to B to the category of cylinders from A prime to B prime. And that's defined by this push out diagram on the slide. So that's just a push out in the category of simplicial sets. So if X is my cylinder from A to B, then I've got inclusion of the fibers. So it gives a map from the disjoint union A plus B to X. And I just push out, I'll take code-base change of that map along the disjoint union of my two maps U and V. And this defines the so-called push-forward functor from the category of cylinders from A to B to the category of cylinders from A prime to B prime. And the technical result we need is that if my morphisms U and V are weak categorical equivalences in the category of simplicial sets, then we want that push-forward functor to firstly preserve weak categorical equivalences, and secondly to reflect ambivariant equivalences, by which I mean if a map in SIL AB is sent to an ambivariant equivalence in SIL of A prime B prime, it should be an ambivariant equivalence to begin with. Now, the proof of this first half, just that push forward preserves weak categorical equivalences, that's very easy and straightforward, nothing tricky there. But the proof of B, this push forward reflecting ambivariant equivalences, this is much harder. And this is really the technical core of the proof, and this requires quite a lot of business. But I'll describe sort of the key ingredients that go into the proof of this step 4B in a couple of slides. But let's suppose that we have proved this. We know that push forward along weak equivalences, weak categorical equivalences, preserves weak categorical equivalences and reflects ambivariant equivalences. So now we're able to make the final parts of the argument. So remember, let's just run through the argument again. So we constructed this other model structure, the ambivariant model structure on SIL-AB, in which the conjecture was true by fiat. So it suffices to show that that model structure coincides with the Joyal model structure by some basic model category sort of reasoning. It suffices to show that every weak categorical equivalence in this category of cylinders is in fact an ambivariant equivalence. And so we'll prove that using both this change of base technical results proved in step 4 and this fact that the conjecture is true when A and B are quasi-categories. So what we do, we first take a pair of, so we've got our simplicial sets A and B, we now sort of replace them by quasi-categories. So we're able, for any simplicial set, there's A, I can always produce a quasi-category A primed and some weak categorical equivalence from A to A prime. And so I do that for both of my simplicial sets A and B. So I now have a pair of weak categorical equivalences in the category of simplicial sets, going from my pair of simplicial sets to a pair of quasi-categories. So I can push forward cylinders along that pair of morphisms. So suppose I've got a morphism of cylinders in this category SIL-AB, that's a weak categorical equivalence. So I want to prove that it's an ambivariant equivalence. Well, I take this push forward. I know that push forward preserves weak categorical equivalence by the easy part of step 4. And well, that's a now weak categorical equivalence in SIL of A prime to B prime, but A prime and B prime are quasi-categories. And I know in that case that these two model structures coincide, so the map's a weak categorical equivalence if and only if it's an ambivariant equivalence. So I've proven that the push forward of my original map is an ambivariant equivalence. And by the hard part of step 4, I know that push forward along a pair of weak categorical equivalences reflects ambivariant equivalences. So I conclude that my original map was an ambivariant equivalence. And that's the argument. By these various steps, we have proved Joyal's cylinder conjecture, so we are entitled to state it as the theorem now. So to reiterate, so we proved for an arbitrary pair of simplicial sets A and B that in this Joyal model structure on SIL-AB, the one created from the model structure of the quasi-categories, an object X, a cylinder X is fibrant if and only if that canonical map to the join is an inner fibration, and moreover, that a morphism between fibrant objects is a fibration in this model structure if and only if it is an inner fibration. So that's the logic of the argument. Now, the hard part was in this step 4B, proving that push forward of cylinders along weak categorical equivalences reflects ambivariant equivalences. Now, I'm not going to be able to go through the argument with you, but let me just give you a few of the key ingredients in the proof. So the first is that observation of Joyal, which is that cylinders are a pre-sheaf category. Now, it's not quite the pre-sheaf category that we'll end up reasoning with, but another equivalent functor category. So recall that for any simplicial set B, the category of simplicial sets over B is a functor category, is a pre-sheaf category. It's the category of pre-sheaves over the category of simplices of B. So combining these two equivalences, we get an equivalence between the category of cylinders from A to B and the category of functors, the category of contravariant functors from the category of simplices of A to the slice category of simplicial sets over B. And under this equivalence, this ambivariant model structure on SIL-AB is going to correspond to some model structure on the functor category. And a large part of the argument is just figuring out what that model structure on the functor category is. So to describe what that model structure on the functor category is, first I'll recall a few things. So firstly, on this slice category of simplicial sets over some simplicial set B, there's this covariant model structure due to Joyal. And so this is characterized by its cofibrations being the monomorphisms and its fibrant objects being the left fibrations with codomain B. So these are those maps of simplicial sets which have the weightlifting property with respect to the left Horn inclusions, you might say. So what role does this model category play in quasi-category theory? This sort of can be thought of as the it's meant to be equivalent to the category of infinity category of functors from B to the infinity category of infinity groupoids. So if you like, it's playing the role of the infinity category of pre-sheaves over B op. Anyway, that's just a bit of sort of motivation that doesn't really play a role in the proof. But so we've got this covariant model structure, which is this fundamental part of quasi-category theory. Just another little bit of terminology that I'll need is that there's these so-called final vertex inclusions in the category of simplices of any simplicial set. So for a simplicial set A, for each for every simplex in A, that is every object of the category of simplices, I have this final vertex inclusion. So there's any simplex has a final vertex, and I can just take the inclusion map of that final vertex. So this gives this class of maps in the category of simplices of A called the final vertex inclusions. Okay, now the statement of the theorem is giving that description of what model structure in this functor category does the ambivariant model structure on cylinders corresponds to. And well, I'm going to have to throw a bunch of buzzwords at you, but I'll give you a sort of interpretation in a moment. So what this model structure corresponds to is, well, firstly, so let's build it up. So on the category of simplicial sets over B, we've got this covariant model structure. So on the functor category of covariant functors from the category of simplices of A to this comma category, this slice category of simplicial sets over B, I can form the Reedy model structure with respect to that covariant model structure on simplicial sets over B. And then I can take a Bausfield localization of that Reedy model structure with respect to the final vertex inclusions in my indexing category of the category of simplices of A. Now, of course, this proof takes many pages, but a lot of it's fairly straightforward. One of the key ingredients, let me just mention, is a result of Danny Stevenson, which is sort of an analog of other results of Joyal and Tierney, which gives another characterization of the class of right anodyne maps of simplicial sets as the smallest weakly saturated class of monomorphisms in simplicial sets, satisfying the right cancellation property, and which contains the final vertex inclusions. Once you have that, the rest is sort of fairly straightforward, following the kind of argument of Joyal and Tierney in their paper, in which they compare quasi-categories and complete SQL spaces. Now, perhaps I should give some kind of moral for what this model structure in this functor category means. So I said that what I'm about to say isn't part of the proof, this is just something you might keep in the back of your mind as a heuristic. So the category of simplicial sets over B, I said, is sort of, with this covariant model structure, sort of presents the infinity category of functors from B to the infinity category of infinity groupoids. Now, the fibrant objects, if you like, in this Bausfield localization on this functor category, these are the functors from the category of contravariant functors from the category of simplices over A into that infinity functor category, functor infinity category, which invert these final vertex inclusions. Now, another very important result of quasi-category theory is that if I take the category of simplices of a simplicial set and I localize that in the infinity categorical sense at these final vertex inclusions, I get the simplicial set A, or rather the quasi-category or infinity category that it presents. So putting together all those things, one can think about this model structure on this functor category as presenting the functor infinity category, or the infinity category of functors from A op into the functor infinity category B to infinity groupoids, or by exponential transposition, this is the functor infinity category from A op times B into infinity groupoids, which is what you would call a profunctor in infinity category theory. So this theorem really gives us a way to see these cylinders as really being profunctors in the infinity categorical sense, which goes back to our very first motivation for this definition of cylinders as an analog of the collage of profunctors from ordinary category theory. Anyway, so that's just a bit of heuristic there. Now, returning to the proof, or the ingredients of this proof of step 4b, this push forward of cylinders along weak equivalences reflecting ambivariant equivalences. The key ingredients are this theorem here at the top, and also a theorem at the bottom of Joyal, which is that if I've got a weak categorical equivalence, I can define this push forward functor, which is just defined by composition, from the slice category of simplicial sets over B to simplicial sets over B prime. Now that functor preserves and reflects the weak equivalences of the covariant model structures. This is a very fundamental and quite difficult theorem of Joyal. So those two ingredients are the important technical parts of this proof, of this technical step 4b in our argument. Okay, so that's the overview of the argument of my proof of Joyal's cylinder conjecture. Now, here's a very important corollary to the conjecture. So recall that the way we proved this conjecture was by constructing this other ambivariant model structure on CIL-AB about which we proved a bunch of things. And then we showed that right at the end that, well, that model structure is the same as the Joyal model structure on CIL-AB. And so in particular, anything that we proved along the way about that ambivariant model structure is true also of the Joyal model structure because they're the same model structure. So in particular, that theorem from the top of the previous slide, I can now state as a theorem about the Joyal model structure on CIL-AB, which is that under this equivalence between CIL-AB and that's certain functor category, the Joyal model structure on CIL-AB corresponds to that. That's the localization of a reading model structure defined with respect to this covariant model structure. And so far in my experience, I found that it's really this corollary to Joyal's cylinder conjecture that is what I use in applications. So if you like, it's just a restatement of, or a reinterpretation of Joyal's cylinder conjecture as saying that Joyal's model structure on CIL-AB corresponds under this equivalence to some model structure described in this way. All right, so that is the end of section 2. Let me again pause for any questions that people might have about that section.
You probably have a
I'll move on. So, go on.
Well, I just want to say you probably have a misprint
Probably
in the second sentence in your page because you repeat.
Yes, I've written ambivariant twice. Yes, thank you. Which makes me worry if I didn't write the same thing in the paper. But yeah, so indeed, yeah, what I mean to say is everything we've proved about the ambivariant model structure on CIL-AB is also true of the Joyal model structure on CIL-AB. Yeah, thank you.
Yeah.
I've got a quick question, if you don't mind. So you have this CIL-AB category, and sort of like, you can think of this as functors from A into presheaves on B, sort of.
Yep.
Morally, right?
Oh, well, sort of the other way around. The sort of variance issue. But
yeah. Okay. Yeah. Flipping everything around. Anyway, so what if you looked at presheaves of categories on B, sort of like Cartesian fibrations? And I know that that's not exactly what you've done here, but does that actually have an interpretation?
Well, you would sort of want these to correspond to, I guess, even the Grothendieck Cartesian fibrations, something like that. But whether there's a sort of correspondence kind of interpretation, yeah, I'm not sure. I don't really have anything to say about that right now. Yeah. I have, I don't know, for the interested reader, I've checked and I didn't make the same misprint in the paper. That's just on the slides that Jayal pointed out. Okay. All right, so let's give an example of an application of this Joyal conjecture. So we can use this to give an easy proof of a characterization of the covariant equivalences, that is the weak equivalences in the covariant model structure, due to Lurie. So in chapter 2 of higher topos theory, Lurie gives this alternative definition or a alternative characterization of the covariant equivalences, which I'll describe on this slide. So let B be a simplicial set. Lurie describes this left cone functor, which goes from the category of simplicial sets over B to the category of simplicial sets. And so this is defined by this push out. If I've got some simplicial set X over B by this map P, then I simply take this push out here. So I include X into its left cone join, as Andre was describing earlier. We can think of this joining with a point as being a cone over X. And we just take this push out here. And Lurie essentially defines, or if you like, characterizes the covariant equivalences in that category of simplicial sets over B to be those maps which are sent by this left cone functor to weak categorical equivalences in the category of simplicial sets. I've called this a theorem rather than a definition because Lurie and Joyal give different definitions of covariant equivalences. So the one that I use in the paper is the Joyal definition. So Lurie proves that these two definitions are equivalent. And so I've stated this is a theorem that of Lurie that a map in simplicial sets over B is a covariant equivalence if and only if it's sent by this left cone functor to a weak categorical equivalence. And Lurie proves this as a consequence of the straightening unstraightening theorem, which is a very heavy-duty, technical, and difficult theorem. But we will, and we can, using this our proof of Joyal's cylinder conjecture, in particular that what I was calling the main corollary to Joyal's cylinder conjecture, to give a much easier proof of this characterization of the covariant equivalences. So let's do so now. So the first thing to observe is that that left cone functor from simplicial sets over B to simplicial sets factors through this category of cylinders from the zero simplex, delta zero, into B. And this is very easy just to read off from the formula. So let me now use this notation C left triangle to denote this first factor, the functor from simplicial sets over B, to cylinders from delta zero to B. And what we can prove using that main corollary of the Joyal cylinder conjecture is that this left cone functor is in fact the left part of the equivalent equivalence between the the covariant model structure on simplicial sets over B and the Joyal model structure on this category of cylinders from delta zero to B. Now, how do we prove that? Well, this main corollary to Joyal's cylinder conjecture concerned this equivalence between sil AB and a certain functor category. Well, in this case, when A is delta naught, that equivalence is between cylinders from delta naught to B and just the category of simplicial objects in the category of simplicial sets over B. And the statement of that main corollary is that this Joyal model structure on cylinders from delta naught to B corresponds to what has been called the canonical model structure on that functor category with respect to the covariant model structure on simplicial sets over B. So what is that? It's the localization of the Reedy model structure on that functor category with respect to the covariant model structure on simplicial sets over B, whose local objects are the weakly constant ones. They're those functors which send all maps in delta to weak equivalences, to covariant equivalences in this case. So if you like, this is the model structure whose cofibrations are the monomorphisms and whose fibrant objects are what are sometimes called simplicial resolutions of objects in simplicial sets over B. So they're the weakly constant, Reedy fibrant simplicial objects in the covariant model structure on simplicial sets over B. Now, it's a very standard fact and not at all hard to prove fact that well, given certain model structures, but in particular given this model category of model structure, this covariant model structure on simplicial sets over B, the constant functor from that category to the category of simplicial objects in that category, which just sends an object to the constant simplicial object at that object. This constant functor is a left equivalent equivalence. It's the left part of the equivalent equivalence between the covariant model structure on simplicial sets over B and this so-called canonical model structure, whose fibrant objects are the simplicial resolutions. So I've made a reference to a paper of Resk, Schrader, and Shipley where this situation is studied. And so that's just, you know, a consequence of this main corollary to Joyal's model structure together with a very standard piece of model category theory, that we get that this left cone functor is the left part of equivalence. And so we can just read right off from that theorem Lurie's characterization of covariant equivalences. So why is that? Well, this is a left Quillen equivalence. And so it preserves and reflects weak equivalences between cofibrant objects, but well, every object is cofibrant in these model structures. So we can just say that this functor preserves and reflects weak equivalences. Now, it's also true that the second functor in this top line, this forgetful functor from cylinders from delta naught to B down to simplicial sets, that also preserved and reflects weak equivalences. That is, by definition, a map in that category of cylinders is a weak equivalence in the Joyal model structure, if and only if its underlying map of simplicial sets is a weak categorical equivalence. So we read off directly from this theorem that a map in simplicial sets over B is a covariant equivalence, if and only if this left cone functor sends it to a weak categorical equivalence. And that's the conclusion of my talk. So thank you very much for your attention.